Welcome everyone, and thank you all for joining us. My name is Max Odkins. I'm an environmental scientist with the Fire and Resource Assessment Program here at CAL FIRE, and I'm very excited to have you here today for this presentation. Space lasers don't ignite wildfires, but they can help monitor fuels and reduce risk. We have with us today Drs. Matthew Clark from Sonoma State University and Christopher Hakkenberg from Northern Arizona University. I'll introduce them in full shortly. But before we do that, I do have some brief housekeeping. As I mentioned, this webinar is being recorded. The recording will be posted on our webpage. There's a QR code on the screen that takes you to our webinars and events page, where you can find recordings of previous webinars, as well as sign up for email notifications about upcoming webinars. We will have a Q&A session at the end of this presentation. So please, at any point during the presentation, type your questions into the chat, and we'll get to them when we get to the end of the presentation. You can also raise your hand and use that feature. We'll also call on folks who have their hands raised and let you unmute to ask your own questions if you'd prefer when we get to that Q&A session at the end. A quick word about the Forest Health Research Program. That is the research program that supports this research as well as many other research projects throughout the state. Our mission is to identify and prioritize research topics that are important to forest health and fire science within the state of California, to fund those scientific studies, particularly studies that support forest managers and policymakers. And we to ensure that that scientific information is readily available and shared with folks who can use it. And in addition, we are working to support the goals of the California Wildfire and Forest Resilience Action Plan, as well as other important state plans. To date, we have funded 89 competitive grants for about $31 million. And a quick update on our recent solicitation that was open. We have now closed our solicitation that was open for concept proposals, and those concept proposals are now in review. We expect our next solicitation to open next fall. That should say fall of 2025. Apologies for the typo there. You can find more information and sign up for updates on our website. The URL is listed on the screen, as well as a QR code that will take you straight to the Forest Health Research Program website. With that, I would like to introduce our presenters today. We have with us Dr. Matt Clark, who is a professor in geography, environment, and planning at Sonoma State University. His research is focused on using novel forms of remote sensing for monitoring biodiversity, assessing land change, and helping conservation and land management. And we also have Dr. Chris Hakkenberg, who is an assistant research professor at Northern Arizona University. He is a remote sensing ecologist who examines cross-scale patterns and processes among forest structure, wildfire dynamics, and biodiversity. Thank you very much for being with us here to present your research. Please take it away, Matt and Chris.
Okay, let's see, let me get this going. How's that?
Looks good.
Okay, great. Well, first of all, thanks for having us here to present our research, and thanks to the CAL FIRE Forest Health Research Program for funding us. This is we're a couple years into this grant, and we're excited to present some research that is in publication. So we're going to tag team this talk, and I'm going to talk about some research that's in revision right now in remote sensing environment, and then Chris will talk about his paper that just came out. And so we're excited to present this, and we'll also finish off with some directions on where we're going in the grant. I also just want to note that Chris is a principal investigator of a new NASA grant that was funded, which puts us on the GEDI science team, the second iteration of that. And so we have a whole research agenda that's going to continue to use GEDI going forward. And I'm having trouble advancing. Hang on a second. There we go. Okay. Okay, so California fire regimes and really the whole US West are changing rapidly. We're starting to see more higher severity fires and over larger extents. And this is due to multiple factors that are all interconnected. But there's been a century of fire suppression that's increased fuel loads. There's changes in climate leading to more aridity and higher temperatures that makes our forest prime for more severe fires, as well as tree mortality and ignitions happening during times of extreme fire weather, like when the winds are blowing, at high velocity. And all these factors are coming together. When all the switches are on, we tend to get these, larger fires with higher severity. And we need tools to be able to kind of evaluate, monitor these fires, the impacts of fire over large extents, in our large state that we have. And this will help us track vegetation regrowth, maybe type conversion, like going from a forest to a shrublands, as well as identify areas that are at risk of higher fire severity so we can direct our resources efficiently. For example, doing prescribed burns or thinning treatments. So the workhorse product that we've used for broad scale analyses of fire severity is from this monitoring trends and burn severity product. And this is by the federal government, and they're produced after fires in the United States. It's based on the Landsat satellite. It's been around for decades in various iterations. And it's really nice in that it does provide a deep historical record of fire severity. And typically it measures continuous fire severity, as I'm going to talk about in a minute, but researchers tend to break this continuous fire severity into these classes like low, moderate, and high. And those breaks, where you put the breaks, depends on the fire, depends on the ecosystems, and there's some kind of art and science to that. So a little remote sensing 101 here. I'm a remote sensing professor, so I got to do this. But Landsat is, like I mentioned, it's been around a long time, and it's measuring reflected light. Okay, so with green vegetation, healthy vegetation, like this green spectrum over here, you tend to get a lot of near infrared reflectance from scattering of photons in the leaf tissues. And you get absorption in the shortwave infrared, where it says SWIR there, in green vegetation. That's the absorption causes less reflectance. The absorption is from water in the foliage. When you get a fire and you get like scorch or char or just consumption of the foliage, then you get decreased NIR because there's less scattering. Also, with less water content in the canopy, you get higher SWIR. And so we use this normalized burn ratio. This is what MTBS is based off of, is using an NBR, which is a contrast between near and SWIR. And what they do is they take a pre-fire growing season image, like in July, and a post-fire image in the year after the fire, and subtract the two, so pre-fire minus post-fire. DMBR will go up with if it's green veg, but it goes down, it goes negative when it's burned. So if you subtract the two, a negative minus negative for post-fire high severity will give you a higher DMBR, that is delta, the normalized burn ratio. So higher DMBR, higher burn severity. Just remember that. That's the key point. If you think of a Landsat pixel, which is 30 meters, it's really measuring the reflected light off the top of the canopy. And so if you have high canopy closure and maybe a light fire like a prescribed burn, you might get the whole understory, charred, consumed fuels, ladder fuels may be consumed. But if the canopy remains green, the sensor doesn't really detect that unless there's gaps. It's really just getting the upper canopy reflectance. So it will just show, low DMBR, even if there has been a burn underneath that has removed vegetation. But moderate severity fires might have some scorched trees, maybe complete, tree mortality, maybe more gaps opened up, and you'll get increased DMBR. And then high severity is, a complete change in spectral properties. More background is in the spectral signature. And and that's going to, completely change the spectral response and get a difference, a really strong DMBR measurement. Now, this is done, like I mentioned, pre-fire and post-fire. And as you start heading towards after a fire, you get the understory greening up, maybe grass, if you think about one of our oak woodlands. And you also get epicormic sprouting, basal sprouting, all that's happening over the year after the fire. And that green up will change the signal. So even a high severity fire might show some kind of green up that lowers its effective severity as far as Landsat's concerned, even though the vegetation is mostly burned. And then as you head into summer, which is when they typically get the post-fire image, then if you're looking at say oak woodland, the grass browns down and you get senesced grass in the signal. All this is to say it's a very complicated signal. It's not always dependent on the actual physical structural changes that have happened. A lot of it depends on the actual reflective properties based on the biochemistry of the upper canopy and the gap fraction canopy openness of that forest. So LIDAR from an airborne sensor like an airplane is wonderful data in that it actually measures physical structure. Now, spectral properties do influence it, but really it's like a direct measure of the structure of the forest. If you do a profile through it, you get penetration of the laser light into the canopy and down lower. There is some diminishing of the signal as the LIDAR, the photons go down into the canopy, but this is an active sensor pulsing out laser light, and it gets you ground returns as well as some ladder fuels and other kind of sub-canopy information. Now, it's wonderful stuff to have, but if you want to do kind of fire severity research with it, then you need to have at least two time periods measured. And that's where it gets difficult. There's not a lot of airborne LIDAR data available. We're lucky in the state of California that we just got some new coverage over like the Sierra Nevadas and the Northwest that do provide a lot of bitemporal LIDAR acquisitions for us. But there's kind of slow rollout of these data products. They're very expensive. They don't happen very often. And even when you get bitemporal measurements, they tend to be many years apart and not right after the fire. So we need a new technology that can help us get more timely measurements for a structure. And that's where the spaceborne LIDAR comes in. And we're going to be talking about GEDI, which is a NASA mission on the space station. It's temporarily parked there. It's meant to be a kind of an experimental sensor to demonstrate the technology before it gets put into a satellite. And these data are different than what you're used to with airborne LIDAR in that it's large footprints, 25-meter diameter, and the sensor's scanning on the space station on these tracks, and the tracks rarely overlap completely on top of each other, but there's crisscrossing that happens, and within that footprint you're getting basically a vertical height profile. Think of it like a vertical height histogram, and Chris is going to talk more about that in his slides. So the goal of our project is to predict wildfire severity as measured by DMBR, using pre-fire GEDI forest structure, as well as other drivers that may influence fire severity. And Chris is going to talk about that. So he'll talk about number one, and then I'm going to talk about number two, and that is assessing wildfire severity in terms of the change in GEDI forest structure as measured by the sensor itself. So like the physical change measured by GEDI within wildfires. Now we have future research that's ongoing, working on treatments, and we're also just mention what we're doing with interpolating GEDI to make continuous surfaces that can allow us to get wildfire risk maps, as well as compare those kinds of maps to existing CAL FIRE products. So from there, I'm going to pass it on over to Chris.
Okay.
Looks good, Chris.
Great. Thanks, Matt. That was awesome. And I learned some stuff myself too, just by seeing those cool graphics. So yeah, thanks. With that introduction, I'll just plunge into this new paper recently published on ladder fuels with some of our co-authors here. And essentially what we're thinking about here is this familiar to all of you, I'm sure, fire behavior triangle. Now, of course, it's context dependent. There are many chance factors that can change this and the way that these different components interact with each other. But generally speaking, weather, topography, and fuel interact to control wildfire severity, or so the theory goes. However, unlike topography and weather, and I have a few of these examples here of weather being evapotranspiration, ET there, vapor pressure deficit, VPD, or wind speed, and topography here is slope. Only fuels can be actively managed. These other things are essentially dictated to us. So as Matt explained in the introduction, how do we better account for these fuels? Well, traditionally, we've used two-dimensional optical imagery, something like Landsat. It's great. That's a workhorse satellite and wonderful imagery. However, it essentially only gives us cover. We're dealing with reflectance here. After all, we're not getting three-dimensional structure. So we do not know the height. We do not know what's going on in the sub-canopy like lidar can give us. Well, we've been using airborne lidar for decades now, as Matt explained, but it has limited spatial coverage. It has high costs, slow data delivery times, inconsistency among flights, sensors, and product. As Matt pointed out, sometimes it's not entirely timely in relation to pre-fire and post-fire to be able to capture that change. Finally, we have simulations and modeled data sets, for example, Wildfire. These are great, but it does have issues with vertical accuracy and precision, as well as limited temporal cadence. So in the gap comes GEDI, and you already have the background on GEDI. So here you can see a quick example of what we're talking about, whereas airborne LiDAR is continuous in space, GEDI is discrete samples of 25-meter footprints. You can see in that figure A what that looks like on a landscape. This happens to be the area outside of Santa Cruz before the CZU complex fire, and those are redwoods. In the panel B, you can see what a redwood looks like with ALS, up to 80 meters in height. It definitely helps to recreate the form of the tree. You can see those branches. And on the extreme right there, you can see what the equivalent GEDI signal is. So this is a waveform. So instead of that realistic image of a tree, we are actually just contending with this singular waveform from which we can characterize things like the top of the canopy, the mid-story, or the ground. So this is an issue that we have to use statistics to be able to contend with, as is the issue of the fact that it is not continuous in space and there are discrete samples with interstitial gaps that remain unsampled. So in this study, we derived 4 metrics for fuel structure. I split these between canopy volumes and vertical continuity. These categories aren't hard and fast, they're just a general rubric. So the canopy volumes, we have biomass as above ground biomass and canopy height is the 98th percentile. For vertical continuity, we have layering, which is just the number of distinct modes in that waveform we were just looking at. And ecologically speaking, you can think of that as canopy layering. Finally, we have this definition of ladder fuels. This definition is specific to GEDI. I know there's going to be a lot of definitions of ladder fuels out there, but the one that we found most effective was the mean PAI under 10 meters for a canopy that goes over 10 meters. Now, PAI is plant area index. You can think of that as the total amount of biomass as reflected on the ground. So a common equivalent would be the leaf area index. This takes account of non-photosynthetic material as well, which includes branches. So you can see here from these 4 profiles that whereas biomass and canopy height in these 3 different categories of high, mid, and low structure, with that high, you can imagine dug for a redwood. With that low structural profile, you could imagine maybe like a lower statured oak. You can see that that large amount of the biomass actually comes in with those higher PAI or biomass layers high up into the canopy as much as 45 meters here. You see the same with canopy height. It's no surprise that there's more biomass higher in the tree for trees that are taller. We see the same thing with layering. The number of modes is going to be related to how tall the tree is. And then finally, ladder fuels on the right, we see a very different profile. And what this is saying is that forest stands that have high ladder fuels are not necessarily the tallest. They all kind of have an equivalent amount of biomass at that 45-meter mark, but below 10 meters, these forests have large amounts of biomass. So the study questions here is, what is the relationship between these GEDI-derived fuel structure metrics and what we've seen on the in wildfire severity from the MTBS data set? How does this relationship change across these topographic and weather gradients? And what are the threshold values in those gradients that constrain the relationship? So there's more results coming, but I'm just going to quickly describe the study and the main results. And I would invite you to read the study for the whole shebang. But the study area here is these three regions in Northern California, 42 large wildfires from 2019 to 2021. If you look at all of the high quality filtered GEDI shots, the sample size is 830,000. And that actually started off at 2 million. And we really did filter these for the best available leaf-on data. The coincident data that we use to make these comparisons is severity, which is DNVR, which Matt described. Topography is slope. Weather is ET, VPD, and wind speed. And I just described the fuel structure metrics. There's a lot of kind of complicated statistics, which I can explain or answer any questions for offline, but kind of long story short, this is a mixed model that intrinsically includes spatial autocorrelation and uses spatial blocking to prevent the inflation of air. So this is just a quick look at what those footprints look like on the ground. This is a linear lattice-like structure of these GEDI samples. And this is the result number one. So this is the question, what is the basic relationship between fuels and severity? And this may not surprise some people on this call, but what we see is a significant positive concave down relationship. If we look in panel A, that's a kind of non-parametric model, whereas B is a parametric model. Both of them tell us the same thing, that the more fuels, the higher severity, up to a point. And then there are some forests that have the highest amount of fuels, as we define by biomass or height and these other metrics. And then it actually ends up being associated with lower severity levels. Now, we didn't test why this is, but we can speculate, and we can talk about that in the Q&A. The next major result is looking at the partial and interactive effects of this relationship between fuel structure, topography, weather, and severity. By partial effects, I mean what remains after accounting for everything else. So what we can see here, to take biomass as an example, if you look at that panel A in the top, is that after accounting for topography and weather, which are the 4 different variables on the right, and their interaction, we see that biomass is positively related to fuel structure. This is what we saw in the last result, minus that concave down. If we look at topography and weather, we see that these elements tend to have a positive effect on severity, which is something that's probably not unexpected to this crowd. Higher slopes lead to higher severity, for example, higher winds, higher severity. But what is interesting is this interaction effect. And the interaction effect is negative. And what that is saying is that this relationship between biomass, for example, in the top row, and severity actually declines where topo weather conditions increase. So you could think about this as an example of as where there are extremely high wind speeds, biomass has less of a positive effect on severity. In other words, the wind is the primary determinant or a larger determinant of severity than biomass. So it doesn't really matter if it's high biomass or low biomass, it's going to burn. Now we can see this in a different way. This is essentially the same result, but just using a new way to present this data. And so if you look at each of these 4 columns, you'll see that in 4 columns and 4 rows, that there's a black dot with error bars. That's the same result that we saw in the prior slide. That's all data. But then we could split that up into 5 equal size intervals for each of the different topo weather conditions. So to take the left for an example, you can split the slope up all 830,000 samples evenly into these 5 different slope categories. And what we can see, for example, for biomass, is that there is this relationship such that with slopes above 20 degrees, the relationship between biomass and severity is no longer significant. In other words, the slope overwhelms the signal of biomass. We see the same for VPD above 3.2 kilopascals, ET above 1 millimeter every 8 days, and wind speeds above 9.3 meters per second. If we go down, we see a very similar profile for canopy height. Going down again to canopy layering, we see now that it's ET and wind speed that are being overwhelmed, but layering is actually consistently predicting fuels across slopes and VPD. And finally, for ladder fuels, we see that in all 4 cases, regardless of the topo weather conditions, ladder fuels are significantly predicting these wildfire severity patterns. Now, I'm just going to conclude, and again, I can take more questions in the Q&A, but this study confirms that GEDI seems to be working for large-scale consistent forest structure characterization, and that this relationship between structure and severity is positive and concave down. With GEDI, we're able to get more than just canopy heights, and we can get things like ladder fuels. Fuel volumes, by which I mean things like biomass and height, are decoupled from severity in these extreme conditions. And by extreme, we've defined these specific threshold values. However, vertical continuity metrics like ladder fuels predict severity even in extreme conditions. And the converse of this is that sparse understories were uniformly associated with lower severity values. So hopefully this will point in the direction of more research and applications for modeling wildfire hazard, containment strategies, and especially for treatment interventions that target ladder fuels versus the entire canopy. With that, I will stop sharing and hand it back over to Matt.
Sorry. Hang on. Okay, I'm getting there. Just gotta find my Teams thing. Okay. There we go. Oh. Somehow I ended up on Chris's slides again. Sorry about that. I'm just gonna roll through his slides. I had it queued up, but then somehow it's bringing everything back again. Okay. Whoosh. All right, do we see my slide?
Yes, it looks good.
Okay, good. All right. All right, so going to now talk about looking at fire severity in terms of GEDI change. So looking at pre versus post-fire differences in GEDI metrics. And using that as kind of an assessment of burn severity. So it's actually like a biophysical assessment of burn severity that's not dependent on DMBR. And this is now in revision of remote sensing environment. And I've got a preprint if anybody wants to look at it. So in my models, you're going to see I'm going to be talking about GEDI change in terms of post-fire minus pre-fire change. So if you have, like, say, high biomass before the fire and then you lose biomass after the fire, this will go negative. So negative change indicates that you're losing some fuels, either it's ladder fuels or biomass or cover. And the goals here of this paper are to first just establish that GEDI forest structure is detecting changes in burn areas with respect to a control area. This is a classic kind of ANOVA, repeat measure ANOVA with a treatment and a control. And then the next part of the study is to assess how change in structure as measured by GEDI metrics within the burned area are related to various predictors. And this is just using linear regression. And we have a suite of predictors you just saw in Chris's talk, but I'm going to be really focusing in on pre-fire structure or fuel loads, as well as DNBR as a way to see how DNBR can predict the actual physical change as measured by GEDI. Okay, so there's more metrics than in this paper than what Chris had, and so we've been working in parallel. And Chris has been inventing new metrics along the way, and then there's some that are part of the GEDI kind of standard products that come out. So we have a blend of both, but we have foliage height diversity, end mode, which you saw as layering in Chris's talk, relative heights, which are basically the height at which a certain percentage of the waveform is below that. And so RH98 is like the top of canopy height. RH50 is like the median of the waveform, the height of where the median is. We have cover, biomass, plant area index, as well as what Chris was calling ladder fuels, which is the mean PAI below 10 meters. We have a new metric that came through in the process of looking at all of our data, and it's called the percentage of the waveform below 10 meters. We were just looking to see what's going on with the waveform as you say, have higher severity and open up the canopy. So in this example, I have a really short stature forest. Maybe it's an oak forest. The whole canopy is below 10 meters. And so the whole waveform is below 10 meters. And that's 100% with this measure. So it's just a percentage of the waveform that's below 10 meters of height. Now, if you have a tall forest and then there's a fire that burns the canopy and opens things up, you get more lidar penetration. And so that's going to show up as more of the waveform that's below 10 meters. So taller forests that kind of open up with higher severity, you're going to see a shift of higher percentage below 10 meters. And so this WI less than 10 metric goes up in higher severity fires in taller forests. Okay, so this is again focused in on these study regions. We have 33 fires in this case. And these are fires from 2019 to 2021. And in this case, we're pairing GEDI footprints, as you see in the left panel there. And we also have a control area, which is a 90 meter to 2 kilometer area around the fire perimeters. And the pairing's done by first looking at post-fire footprints and then looking within 45 meters to find nearby footprints. It's rare that we get footprints that are completely pre-fire, post-fire overlap. So we opened it up to look for those footprints that are within 45 meters. We have a 10-meter elevational difference threshold too. So anytime we have a pair that's more than 10-meter elevation apart, we filter those out. Also look at footprints between May and October to eliminate phenological changes. And all told, we have 55,000 of these pre-fire versus post-fire footprint pairs. You can see a lot of them are occurring in conifer forests. If you just look at DNBR severity class, you're taking that MTBS product, we have a lot in moderate and high. But the MTBS doesn't show everything that's happening below the canopy, so take this with a grain of salt of how these are distributed across severity. If you look at the control, it has relatively same proportion of conifer, hardwood, and mixed forests. On the right in B, this is the timing of the post-fire footprints after the fire. And most are within 1 to 2 years, and that's because GEDI's only been operational from 2019. It turned off in 2023 for a while, and then it's been turned back on after a year. So we don't have a lot of post-fire data to actually work with, but this will increase over time as GEDI continues on the space station. Okay, so the first analysis, think of this as a repeated measures ANOVA, just to look at the effects of being in a burned area on GEDI, and pulling out the part that's related to growth between years, between pre-fire and post-fire, just growth that happens from just over that period of time, as well as other kinds of loss due to disturbances like mortality. So the baseline effect is, in this model, is basically being in the control area before the fire. And then if the burned effect in this model is being in burned versus control, but before the fire even happens. So it's pulling out that part of the variance. And we see that it does increase. So the normalized effect is positive, and it's significant, as indicated by solid bars. And this is telling us that there is a difference. There's more of these fuels pre-fire than in outside in the control area. So the control area is not a perfect representation of what was happening when the fire came through within the burned area. But it's okay. We're pulling that part of the variance out and then showing you what is actually due to being in the fire. There's a timing effect, which is just growth or loss due to just not irrespective of the fire happening. And that's relatively small, and a lot of those bars are not significant. But the interaction is what we're really interested in. And this is being in the fire. What is the effect of that on GEDI metrics? And it's negative. And that's because we're doing post minus pre here. We're seeing basically like a decrease in metric values as when you're in a fire. And they're all negative, showing a decrease. There's one positive, and that's at WI less than 10, which we expect to go up after fire. Okay, so this is all just looking at the footprints by themselves and breaking them between burned and control area. If you were to actually like look at the distribution of these variables relative to DMBR burn severity, if you just focus on the high severity here, you can see that DMBR picks up high severity really well. It maps that very well, and our GEDI metrics do as well. There's definitely a shift in going from pre-fire blue to the salmon pink color after the fire. We're seeing a decrease in foliage height diversity, a decrease in canopy cover, a decrease in height, total height of the canopy, RH98, a decrease in what we're calling ladder fuels, this lower PAI, and an increase in this waveform below 10 meters, as we'd expect. Now, this DMBR, it's not so great necessarily for the low severity fires. You're not seeing a lot of change there, but the GEDI, as we'll see, is picking up what's going on under the canopy. Okay, so looking at change in GEDI metrics, post-fire minus pre-fire, related to different predictors. These are univariate regression models. It has spatial autocorrelation of error in it to deal with spatial autocorrelation. So we get a pseudo R squared out of this kind of modeling technique. But you could just think of it as an R squared value, towards one more significant effect. And the main message here is that pre-fire structure fuels, so it's the pre-fire levels of each of these variables, has the strongest relationship to change in GEDI measurements of forest structure. The next strongest predictor is DMBR. So it's not as strong as just using GEDI itself as a predictor of fire severity. In this case, fire severity being just the change in GEDI metrics. If you look at the slopes from these models, you'll see that the pre-fire structure, is more negative. So again, this is post minus pre. So we're seeing, basically it's more pre-fire fuels, more biomass, more cover, a bigger decrease in these metrics. DMBR has similar trends. Similar trends, but less pronounced effect. Now you'll see that WI 10 meters is different. I'm not going to go there. We get into the paper. It's kind of a nuanced explanation that has to do with balance of hardwoods and conifers in short stature forests. But in the interest of time, I'm going to move on to my take-home messages and to say that we've demonstrated that spaceborne lidar metrics do statistically quantify structural changes in California wildfires. There's significant change in burned areas relative to the control areas. We found pre-fire levels of fuels are the strongest predictor of change. And that GEDI, sorry about my advancing here, is really messing up. But the GEDI is more sensitive to structural change than DMBR. And this leads us to new ways of mapping burn severity over large areas and through time with these timely GEDI data, maybe in concert with burn severity as measured by Landsat. So you might see like a hybrid kind of severity informed by Landsat as well as GEDI. Okay, so we're going to talk about our paths forward. I'm going to talk briefly about where we're going with our analysis of treatments. And in this case, we are looking for treatments around California using the FACS and CalMapper database to get information on what kind of treatment happened, and refining the treatment boundaries with Planet 3-meter data, and looking exactly at what time or what year the treatments actually occurred, which are not always the same as what's in these databases. So we're getting refined treatment information and looking at the GEDI footprints that are post and pre-treatment. And this analysis is still in process, so more on that later. And now I'm going to hand it over to Chris, who's going to talk about other upcoming paths forward with GEDI.
Thanks, Matt. Hopefully you can see the screen.
Yep, looks good.
Is that okay? Great. So I'm going to just say one thing really quick about, because the study that I led had this focus on ladder fuels, and just to be clear, those are defined as mean plant area under 10 meters for canopies that are greater than 10 meters. So this is the idea, is that this is propagating fuel from one layer to another one higher, from the ground through the canopy, versus just having PAI below 10 meters, which could just be low stature forests. So this is a vertical fuel propagation. Okay, so the second path forward here is going to be part of our final objective. We did publish some data using an aggregation method. This is available now on Google Earth Engine. I encourage you to check this out if you just want super easy to digest and use near global raster data, which just represents the aggregate of all of those shots in a single pixel. You can see some of the different ways that we aggregated it. This is user-friendly and user-ready data that you can get from Google Earth Engine or the Ordinal DAC. This is kind of what it looks like to get an idea. Of course, we get ground elevation as being the bottom mode of the large footprint waveform, and then we can also get advanced metrics like this one, foliage height diversity, at these 3 different resolutions of 1, 6, and 12 kilometers. You can reach out to me, check out that Nature Scientific Data article, or just do a quick search in the Google Earth Engine search bar. The next one that we are working on, and this is kind of this transition to more of our GEDI science team work, is using the CCDC algorithm to interpolate rasters at a 30-meter resolution. So whereas that prior project is 100% GEDI data alone that's aggregated into a pixel, this is actually using optical data like that from Sentinel and Landsat to be able to have a much finer resolution map of forest structural metrics continuous across the landscape without those gaps that we saw before. Now, of course, what you get here is a mixture of optical and GEDI. So it's not a pure LiDAR signal on the downside, but on the upside, you get a continuous structure in space. And so here you can see one quick application of that, pre and post August complex fire. You can see the height change is pretty remarkable with all those areas in red on the far right showing a height change of 20 meters or more. So one application of this, because we're using this algorithm that it kind of is informed by this ancillary optical data, is that we can hindcast. So we can go back in time to the year 2000 and be able to look at structural change. Now, of course, the further back we go, the more we're kind of extrapolating. So there's going to be larger error associated with this data, but it's still pretty cool and pretty novel. And so here you can see on the right, this is an area in New Mexico, and the red band is represented by the canopy height in 2000, and the green 2010, and the blue is 2020. So you can see from this different from this color mixture that there have been some pretty significant changes to the forest structure over time due to many different causes, natural disturbance, anthropogenic disturbance as well. Finally, I just want to give a plug. We have been selected for phase 1 funding for a new NASA mission called the Earth Dynamics Geodetic Explorer. This is essentially GEDI on steroids. As you can see from that lower panel, we are expecting this to, rather than being discrete samples across the surface of the Earth, we're actually going to be able to scan entire swaths like ALS, but from a standalone freestanding satellite. And so that means we're going to have more continuous horizontal structure that we're going to be able to assess, and we're going to have a much increased coverage. So we're going to be able to, if you can see that bottom row essentially shows what the nominal mission standard is for 2 years of functioning. And GEDI is pretty darn sparse. With EDGE, we're getting close to 80%. So if we are selected for phase 2, which we'll find out in the next year, this would launch in 2030, nominal 2 years, but hopefully this keeps giving us data for many years beyond then. And I will just give a quick shout out that we are including in part of this a special opportunity funding to be able to use EDGE, and in the lead up to EDGE, the launch of EDGE, to be able to target wildfires. And so we've been talking with some folks, and if that's something that is interesting to people on this call, we're going to be putting that proposal together in the next month. We would really like to see this being used for a wildfire application. This just seems really kind of critical to one of its 2 core missions, which is terrestrial systems. Wildfire and fuel structure obviously is important to all of us. And that second core mission or target objective beyond terrestrial is the characterization of the cryosphere, so continental ice sheets and glaciers, and that is completely outside of my own wheelhouse. So with that, I want to thank everyone, and yeah, open the floor to some questions for both Matt and I.
Great. Thank you so much, Chris and Matt. It's wonderful to see your research here. I am going to stop our recording in just a moment and switch over to the Q&A, but I just want to first say one more big thank you for coming and presenting here with us today.
Absolutely. It's been a pleasure.
Thanks. Thanks for inviting us.